Hey Stats 193 students, it's Ariel. I'm going to make another video for you about normal distribution. We will be going over this on Thursday, and this is the point where we're really getting into the nitty-gritty of statistics, and the normal distribution is a tough concept for some students to grasp. So I'm going to make a couple videos on this one. The first video, this one, is just going to be explaining exactly what normal distribution is, why we use it. I'm going to tell you about the bell curve, and then we're going to go a little bit into the empirical rule of statistics of normal distribution. So normal distribution, write that down. Normal distribution plays a very important role in any statistical analysis. I'm taking genetics right now, and we use normal distribution quite frequently. I know that if you're going on in biology or psychology, a lot of statisticians will create normal distribution plots or bell curves for important data that is quantitative. This is because every statistical distribution can be approximated by normal distribution, provided that a large enough sample is taken. It's an important bridge between the discrete and continuous distributions. So this is where our EX meets our Poisson and binomial distribution. This is going to be kind of a forgery of the two of them together. So one equation that I'm not going to write out for you guys, I'm going to sum it up. The equation is on page 164 if you want to look at it. I am just going to write down x and with mu and sigma squared. And I know that a couple of these variables look familiar to you and some of them don't look very familiar. So let's walk through exactly what this means, because this is the bread and butter of normal distribution right here. And what this means is this is saying that our x value for the test, and the squiggly line here is just saying it's part of the expression that it's normally distributed, n. So this portion right here, x is normally distributed. And we're going to continue this in a second once we break down this part right here. We know that this variable here, this is mu, or the mean. So mu equals mean. When I told you that we're going to start using mu more frequently, I definitely meant it, because now with normal distribution, we're always using mu. And sigma squared is our variance. So we're going to continue our expression. X is normally distributed. We're going to say with mean, mu, and variance. Sigma squared. This is what you're going to want to remember when we start doing normal distribution. And this, being able to understand normal distribution, is going to help us when we get into later chapters with hypothesis testing, because this is very similar and it's kind of like a gateway to testing a statistical hypothesis. So now that we've established our expression, x is normally distributed with mean mu and sigma squared variance. This is a model for a continuous variable x. The domain of x is a real line, and it goes from negative infinity to infinity. But the shape of this line is what we're going to talk about next. What does a normal distribution look like? And if you're a visual learner like me, and even if you're not, I always suggest when you're doing these problems to make a bell curve. What a bell curve is, it's a curve that goes up like this. And please excuse my poor drawing capabilities. I am not the most artistic person, to say the least. All right. And we're going to say that 0 is here. The shape up here looks similar to a bell. If I were to just do this, it looks kind of like a bell. It reminds me of The Hunchback of Notre Dame, if any of you are Disney fans. But one cool thing about this that's really going to help us out is if I draw a line right here, there's the same area on this side of my bell curve as there is on this side of my bell curve. If I were to split this right down the middle like I just did, there's the same area on the left as there is on the right. It's symmetrical. If I were to take it on a piece of paper and fold it in half, it would look exactly the same on both sides. So now what we're going to do is we're going to build off of our bell curve. Now that we know that it's symmetrical and it has the same area on both sides of the middle, I'm going to build off of that idea. And what I'm going to do is I'm going to draw my middle line again. I can't even draw a line, look at me. I'm going to draw a middle line again. Now, if we were to go back up here and look at what's involved in normal distribution, the mean is involved. Oops, the mean is involved. And the variance is involved. So I'm going to take that idea back down here. I'm going to think about it in a different way. I'm going to say, okay, if I were to put any value in the middle of my bell curve, what would it be? And I think that, and the correct idea for this is that the curve peaks at the mean. Mu. When you're thinking about this in statistics, when we calculate our mean, we add everything up, we divide it by n, and we get mu. That's going to be where most of our data is. And so it makes sense, it's very logical, to put the mean at the highest point of our bell curve, because that's where most of the data is. The data is all the way up to here. It wouldn't make sense to put our mean, say, over here or over here, because that's not where most of our data is. So our mean is our highest point in our bell curve. And I'm going to get really repetitive with this, but I want you guys to really grasp this concept because we're going to be spending a little bit more time on this, and it is very important that you, out of all of the things that we've learned so far, learn this. So normal distribution, our x values, which we'll talk about later, what our x values are normally distributed, which is what the n stands for, with mean, mu, and sigma squared, variance. And we decided that we were going to draw a bell curve and say that, okay, and the reason I put 0 right here is so that I could instill into you guys that if I were to put a 1 up here and a -1 down here, my area is still going to be the same. If I were to put 2 and 2, My area is still going to be the same on either side of my bell curve. So we've established that the bell curve is symmetrical in this step. Symmetrical. And we came down here and said, okay, I can pull my mean out and I can put it in the middle of my bell curve right here, because most of my data is going to be surrounding my mean. So now let's talk about standard deviation and where that plays a part in this. And we're going to use this bell curve. I'm going to use this bell curve right here. So I'm going to draw some marks in here. I'm going to say, okay, 1, 2, 3, and 1, 2, 3. And I'm going to go in and I'm going to label those points. And I'm going to say that this is going to be 1, this is going to be 2, this is going to be 3, and this is going to be -1, -2, and -3. So we know that our bell curve is symmetrical. There's the same area on both sides of my curve. And there is another variable that we can use and replace our mean, but I'm not going to do that quite yet. I want to establish this idea first, and then we'll switch out the mean. So what these 1, 2, and 3 mean, this 1, 2, and 3 is how many deviations away from the mean are encompassed at that part of the bell curve. And this is what brings us to the empirical rule. Or it's also called the 68, 95, 99 rule. Now bear with me, I know that this is getting a little bit confusing, but we're going to clear it up real fast here. So what this is saying is that here, between 1 and -1, and these are all deviations from the mean. So how many deviations? How many, and they are standard deviations, so how many standard deviations away from the mean are we going? Now, I drew those lines at 1 and -1, and I'm going to shade this in. And now when I look at that, the empirical rule says that if I am encompassing an area from -1 to 1 deviations away from my mean, and we're going to color code this. So here's this one. That means that I can assume that 68% of my data lie in the shaded area. I'm going to give you a second to write that down. Alright. Now, I'm going to use this fun galactic kind of, I don't even know if those are stars or what those are. Anyway, so if we go to up to 2 and down to -2, and I'm just going to shade in this portion, but know that this encompasses the center too. So I'll draw dots in the center that are this color, because this one's going to cover all the way from here to this point on the bell curve. And now when we're broadening our area, we can assume that the percent that lies in that area is going to be substantially more. This is the 95%. Or 95% of the data lie between -2 and +2 deviations away from the mean. And I'm using this language so that it's a little bit easier to grasp in class when Professor Onya uses this language. So I'm trying to kind of break it down, but at the same time, use some of the same terms that you guys aren't struggling so much with that. I did get some feedback that it was a little bit hard to understand them, and it is like a second language in a statistics classroom, but we're all going to make it through. So here, if we come up to 3 and down to -3, and we say that, okay, I'm going to cover this whole area right here, all the way from here, all the way up to here, this is going to be the 99%, or 99% of our data are going to lie between -3 and +3 standard deviations or deviation points away from our mean. And that's the empirical rule. And that's going to help you out when we're doing some of these problems, being able to apply the empirical rule and think to yourself, okay, you know, how right am I with my answer? How many standard deviations am I away from the mean? So now we're going to move on a little bit more, and we're going to go over another variable. I know that there are a bunch more variables to go over. Let's come up here. And this variable that we're going to go over is z. Now I know that Professor Onya is going to explain exactly what z is in the classroom, so if you're concerned about exactly what z is, wait until you go to class, listen intently, and you'll learn exactly what z is. I'm going to show you right now what we use z for and how to apply it. So there's an equation that we use for normal distribution, any normal distribution problems, and it's z equals x minus our mu, our mean, all over sigma, for our standard deviation. Z the letter stands for z-score or z-value, and it stems from a way that statisticians came up to derive probabilities from a very accurate table. And that table is going to be on page 523. So if you want to go to page 523 with me, what you're going to see, and I'm going to do my best to try to draw a couple of columns because we're going to learn a little bit about how to use the table before we do a problem. And we're just going to put that formula, and that z stands for the z-score or the z-value, we're going to put that in our back pockets, or our back pocket. So now when we come over here, you're going to see the Z table on page 523, and you're going to see Z up here, and you're going to see some rows and columns. So along the top, you're going to see 0, 0.01, 0.02, and 0.03, and it's going to go on, but I'm just summing this up just for learning purposes. And at the very beginning, you're going to see negative 3.7, negative 3.6, negative 3.5, negative 3.4, negative 3.3, and I'll go down to negative 3.2. And then I'm not going to write in all of the values for the body of the table. We'll just write a couple. 0, 0, 0, 1, 0, 0, 0, 1, 1, and then let's do all right. So when I was talking about a z-score in the previous problem, what we can do is we can plug in an x value like we did with binomial distribution and Poisson distribution. And if we're given the mean and the standard deviation, we can solve. We can say, okay, I'm going to subtract the mean from my x value that I'm given and divide it by the standard deviation right here. And what I'll get in the end is my z, or my z-score, or you can call it a z-value. Z-score and z-value are exactly the same thing. They're just two different ways of saying it. I always say z-score. So what I'm going to do is I'm going to erase z-value. Now we're just going to use z-score. So now let's go back to the table. Let's say that I've solved for z, and my z equals negative 3.72. Notice that there are 3 digits. We always have or round to 3 digits when we're doing normal distribution and using z, which we are for all of the problems we're doing now for normal distribution. So we're solving for z. We have to have 3 decimal places. This one at the end, it can be a 0, it can be a 1, it can be a 2, it can go on and on. The table's able to accommodate for that, but we have to have 3 digits. So now we solve for the z-value, and this is hypothetically, we haven't done any math yet, and our z-value, or our z-score, was negative 3.72. All of these values here partner up with these values here to make z-scores. And the values in the middle, what I like to call the body in here, those values are probabilities associated with our z-scores. Because Because for normal distribution, we're still solving for probabilities. And we can work backwards. Given a probability, we can solve for a z-score. And we're going to go over that later. First, we're going to use the z-score and learn how to use the table. So, the body of the table gives us probabilities associated with the z-scores. But what do the numbers on the top and the numbers on the side have to do with z-scores? How do I put those two together? This negative 3.7, the first two digits of your z-score are going to be found along this side, the left side of the z-table. So let's locate ours. 3.7 is right here. And this 2 tells us that that's my third digit. It's 1, 2 places after the decimal. So if I were to take this and pull it away from negative 3.7, I would just have it by itself as 0.02. And this I can find right here on the top. This isn't a coincidence. Every single z-score that you solve for is going to be like this. The first two digits are going to be found on the left-hand side of the table, and then the last digit is going to be found by itself at the top of the table. And if you're doubting yourself, and if you're kind of bad at math, what you can do is you can say, okay, I want to make sure I'm right, and I'm going to take negative 3.7 plus 0.02, and it's going to give you negative 3.72. If it doesn't, you've done some math wrong, go back, try it again. I'm going to give you guys a second to process that and write everything down before I continue. So now what we're going to talk about is that body of the table. When I have found my top number and my side number on the table that are associated with my z-score, which make up my z-score, I should say, I'm going to follow them over to where they meet. And these two guys, negative 3.7 and 0.02, they meet right here. And remember what we had said, that the body is the probability associated with each of our z-scores. If we were to solve this equation to get a z-score of negative 3.72, the probability that whatever we're solving for, if say we were doing a problem on how many men buy shoes from DSW shoes, and we solve for a z-score of negative 3.72, we have a probability of 0.0001. So we can concur that not many men are buying shoes from DSW shoes. Such a small probability. But as you work your way through the body of the table, probabilities get larger. And the table in your book goes to page 525, so it's a pretty long table. It goes from negative 3.7 to positive 3.7. And it's going in increments of 0.1. So let's come down here. Oop. So just to recap where we've gone with this, we've determined that normal distribution is where x is normally distributed with mean mu and variance sigma squared. We came down and determined that a bell curve, the sign, the table that represents normal distribution, is symmetrical and has the same area on the top side, the high side, the positive side, whatever you want to call it, up here, as it does on the negative side. we went over the empirical rule and said that 60% of our data are going to lie in this, 68% of our data are going to lie in this shaded area right here, 95% right here, and 99% is going to go all the way from -3 to +3. We came back up here and we learned the equation for Z. We learned what Z is, and we learned what the Z table is, and how to find a probability in the Z table. So now we're going to go back to our Chapter 6 fun information. We're going to make a new bell curve with the information that we have. We're going to bring the empirical rule back, but instead of having the mean at this point right here, we're going to put Z right there and 0. And the mean is at the same spot here. So now if I were to go up to 1, 2, 3, -1, -2, -3. What these are, and this was kind of a poor explanation. I'm going to erase these two. That middle point is still the mean, but this is going to be 0. This whole area, the -3 to +3, is going to be in terms of Z. So let's use our previous example. We had a Z-score of -3.72. I can go on this table and I can draw a line at -3.72, and I'll say -4. Oh, -4 is going to be right here. And -3.72 is about right there. And just to show you what that 0.0001% looks like, that means that this much of the table, my probability for that happening, if it were visually represented on the normal distribution curve, it covers that teeny tiny minuscule little spot right here. That's the area that my data covers, the probability. Now, if my Z-score were +3.72, and here's where it's cool, where when I told you that the table is symmetrical, here is what I mean. If I were to go over to this side of the table, I'm going to put 4 right here, a +4. I'm going to say, okay, my Z-score up here, I have +3.72. That means that all of the area on this side is covered. And that's going to translate to a probability of 0.9999, and I think it goes on and on. So if we were to take, and the probability over here is 0.0001, remember. If we were to take these two associated probabilities, and if we were to add them together, they're going to equal 1. And there's that rule that I talked to you guys about. 1 minus p equals q, and 1 minus q equals p, and probabilities kind of work together in order to help us out. Well, it can be applied to this as well. So, let's move on to a sample problem and try to do it. I'm going to try to find a problem in here that's all right. Let's do example 6.5 together. Example 6.5. I'm going to go over here. Example 6.5 says the heights of mothers X are known to be normally distributed with a mean 65.78 inches and a variance 13.69 inches. Remember in the beginning when I said how this is written out, that X is normally distributed with mu, mean, and sigma squared variance. We can plug in our own information. We can say that X is normally distributed with n 65.78, our mean, and our variance 13.69. This is not an equation. This is just a way that statisticians use to say that this data set is normally distributed. I know that on the exam, Professor Onia might put down, he might just give you this information right here and say, okay, here are several scenarios, find the probability for each scenario. And what you're going to need to discern from this is that this 65.78, that's the mean. And that 13.69, that's the variance, sigma squared. This is something that you need to know. The equation for this is not going to be on the exam because it's that important that you need to remember it. So now let's, just to refresh our memories, write down the equation for Z. Because remember I said for each one of these problems, we're going to have to use a Z-score to find the probability. It's like a stepping stone to find the probability. So Z equals X minus the mu divided by the standard deviation. Now, I have all of the information that I need to make what I like to call my skeleton equation. So I'm going to plug in the variables that I have and see what I'm left with. So I know that Z equals, I don't have an X value quite yet, so I'm going to say X minus, but my mu I know to be 65.78 all over, and here I'm given my variance, but I need to know my standard deviation. I can just take the square root of that. So I can say down here, okay, square root of 13.69, which comes out to be 3.7. Now I have my equation that I'm going to plug my X values into. So let's do A. A for this problem asks us, What is the probability that a height of a mother chosen at random is greater than 61.2 inches? And here, I'm going to write it as greater than 61.2 inches. But I want you guys to get in the habit of using the greater than or less than signs. So here I can translate this into x is greater than 61.2 inches. This is a good point to talk about the alligator system, I feel like. Let's come back up here. So I don't know how your guys' math teachers taught you this, but mine, and I am not a great artist at all, this is my alligator. So say we're going to draw some teeth on this bad boy. When you're using these signs, the greater than or less than symbols, the mouth of the alligator is always going to be opening towards the larger. So this guy, if we were to talk about it in terms of our problem, we're looking for x is greater than 61.2 inches. So this guy is going to be opening his mouth towards x, but then over here, the small side, he's going to be turning his face away from 61.2 inches. He doesn't want it. It's going to be smaller than x. He wants the bigger prey because he's a hungry gator. So now that we've established the greater than and less than symbols, I know it's been a while since some of you guys have used those. I'm going to come back down here and notice I drew my x is greater than, the alligator mouth is opening towards my x, and away from my 61.2 inches. Now that we've established that, we can start plugging values into the equation. So let's go back up to the equation. This system is going to work a lot like Poisson and binomial distribution, where your x values are actually given to you in the problem. You're being told to plug x in. So where it says greater than 61.2 inches, you know that that's your x value. So we're going to say z equals 61.2 inches minus 65.78 inches, all over our standard deviation 3.7. And we're going to solve for our z-score. So when we solve all of this, we're going to find that z is equal to sorry guys, I'm doing the math here. 1.24. I'm sorry, negative 1.24. So There's another rule that I'm going to talk to you guys about, but we are going to find negative 1.24 on the z table. And that, like I said earlier, is going to be on page 573, I believe. No. 523. So we're going to follow the left side down to 1.24. Or down to 1.2, excuse me, negative 1.2. And we're going to go to the right until we see 0.04, because that's the last number. And we get 0.1075. And this is written as the probability of z equals 0.1075. Remember, we get that from the body of the table. But there's a rule about the z-table that I didn't talk about, and that's the z-table is only set up to find values that are less than, not greater than. So any time that it says greater than, we're going to have to do something. We're going to have to subtract our end probability from 1. 1 minus 0.1075. And that's going to give us 0.8925. The reason why we're subtracting 1 is just because of the rule. The z-table is not set up to find anything greater than a certain value. It's set up to find less than a certain value. So what we're doing is, when we solved and we got that 0.1075, we actually unknowingly solved for less than 61.2. And that's why, because we talked about that probability of 1. 1 is the highest probability, and if we subtract from 1, it's going to give us the opposite. And I'm going to write that down because this is another rule that you guys need to know, that the z-table is not set up to find values greater than x. Only less than. And I'm going to leave you guys with that thought for this video. I will continue this problem and a couple other problems in my next video, but I know that this is a lot to digest, so I want to give you guys a little bit of time to not only maybe watch this video again, go through it for yourselves, but to also look at the book, because it is a good resource for you guys, especially if you're looking at the examples that I'm going through with you. I haven't done this stuff in about a year. It's been a year since the last time I did this, so going through the examples is how I learn the materials as well, or refresh my memory on the materials. So try to go through a couple of the examples and just read through. If it's not working for you, try Khan Academy along with my videos. Make sure you're getting in your 6 hours of statistics a week. I know that statistically, actually, there was a test run that in order to be successful in a class, students needed to spend 2 hours outside of class for every hour they spend inside of class. And I feel like that really does hold true for statistics. If you are wanting to work on a couple problems in the back of the chapter, it starts on page 187. We haven't done quite enough to go through an entire problem, but we did solve for greater than. So if you wanted to find a problem that said, find the probability of x being greater than a certain number, you can definitely go through with my video and try to do that. I am going to probably make that other video tonight as well, so watch out for that. Otherwise, have a great night.